Hello, and welcome to Lecture 14, Part 1, where we're going to start a new topic of a rigid body. This corresponds to Goldstein Chapter 4. So, who remembers how many degrees of freedom a rigid body has? A while ago, we figured out that it was 6 degrees of freedom, which come about from 3 translational degrees of freedom and 3 rotational degrees of freedom. So that's where 6 come from. So let us try and build up towards a description of a rigid body in 3D. Let's start with a 2-dimensional case. So suppose we are looking at a vector, let's call it B. And we would like to rotate it. And we're going to rotate it in a weird way. We're going to be rotating it clockwise by an angle phi. So this is going to be vector B prime. So let's try and find the relationship between bx, by, and bx prime and by prime. Using the regular rotational matrix, we can write it out as cosine phi, sine phi, minus sine phi, cosine phi, times bx, by. Hello, buddy. How are you, buddy? So, now that we've figured this out, we can denote this as the rotational matrix Aij. And you can figure out where this comes from by seeing how the rotated components, bx and by, if you were to rotate both of them by an angle phi, how they would project onto the original x and y axis. For instance, if you rotate bx by an angle phi, then it would have contributions along the x-axis of bx times cosine phi, and by rotated by phi will be by times sine phi. So that's where the first row times the column comes from. And then for by prime, we will need to look at the projections of bx rotated onto the y-axis. So if we rotate by angle phi and project on the y-axis, then that would be bx times sine theta with a minus. Exactly, sine phi with a minus. And for by, once we rotate, it will maintain the same sign, but it will be multiplied by cosine. So by will be multiplied by cosine theta. So that's how you can see how to convert the old coordinates to the new coordinates using the rotational matrix. This is called an active transformation. That's because we are actually doing something to the vector. We are rotating the vector. But there are in general 2 types of transformations. There is active transformations, just like this, and there are also passive transformations. So what's the difference? Here we rotate vector, and there we rotate the coordinates. So that is the main difference between these two. So here we get from old vector b the new vector b, whereas when we rotate the coordinates, we rotate x and y's, but the vector stays the same. Here the vector changes position and goes from B to B prime. So if we were to try and write out the passive transformation, then the way we would do that, we would say that B prime of I, so the new coordinates of the same vector, would be Aij times Bj. And in this case, we would rotate things differently. We would take the x and y coordinates, and we would rotate them by an angle phi. So we would have a new x coordinate, and we will have a new y coordinate, and that would be the rotational vector. So you see that the same exact rotational matrix works in both cases, except that the sign of phi changes. Here we rotate it clockwise, and there we rotate counterclockwise. So this is same vector, new coordinates. Great, so now let us move on and ask, what is a vector? And the answer is anything. Well, that wouldn't be a great answer, not very specific, but anything that transforms as a vector after rotating the coordinates. So what does it mean? It means that it's going to be B prime equal to A times B. What is a tensor? Answer, something that transforms like this. Cij prime is going to be equal to Aik times Ajl times Ckl. So you see that there is one rotational matrix per each of the tensor index. So if each of the indexes of the tensor transforms as a vector, then we have gotten a tensor. With this, we are ready to develop some of the machineries in order to figure out how rotations behave in time. And that will be in part 2 of lecture 14. I'm going to see you there. Hello and welcome to part 2 of lecture 14. Let us figure out what is the time derivative of a rotating vector. And let's start with the 2D case first. So suppose that we have gotten our coordinates, x and y, and we would like to rotate vector b. So this is our vector b, and it is rotating, and say we will denote its starting position as b prime. So this is how the vector has rotated. So this b prime is going to be a constant, doesn't change in time, and that is the initial value of b at t equals 0. Okay, so at t equals 0 we start b at b prime, and then we rotate him. Will be a rotational matrix, but look, phi is counted off in the positive direction, whereas rotational matrix in the active approach rotates the vector in the clockwise direction. And here we're rotating it in the counterclockwise direction. So we need to plug in minus phi as an argument for the rotational matrix. So b prime gets rotated counterclockwise and gives us b. So this is our matrix, just where we have switched the sign of phi, so it will look like this. and all of that is multiplying b prime. So this is a of minus phi, and as you notice, this is no different than just the transposition of a of phi, right? So this is then, and this is now, and this was t equals 0. Okay, so let's try and take the time derivative of b dot. What will that be? Because b prime is a constant, we're going to write out that it is going to be a tilde times b prime, all of a dot, and because b prime is a constant, the dot only works on a tilde. And because b prime is going to be the inverse of this times b, and inverse of this is just a, we're going to be able to write b prime as just a times b. Okay, so let's see. What is going to be a tilde dot? Well, a tilde dot, right? A tilde dot is going to be this matrix with a dot times phi dot. So what is this matrix with a dot? Well, it's going to be minus sine, minus cosine, cosine, and minus sine. Let's open up some room over here. That will be multiplied by a, which will be cosine phi, sine phi, minus sine phi, and cosine phi, multiplied by b. And we can then try and perform this multiplication. So what will this be? For the top left, minus sine phi times cosine phi, so it's minus sine phi cosine phi, and plus cosine phi sine phi, so that will be 0. What about this one? Minus sine phi squared minus cosine phi squared, so it will be minus 1. What about this one? It will be cosine phi squared plus sine phi squared, 1. And what will be this bottom one? Will be cosine phi times sine phi minus sine phi cosine phi, 0. So what we've gotten is this transformation. And this can be represented as a z vector that's sticking out of the plane. Hat means it's a unit vector sticking in that direction. And we can multiply that as a cross product by our vector b. You can see that by writing out b as bx times x plus by times y. And you can see that indeed the result will be z cross x will give you, it will be yzx, it will be minus y, right? So indeed it will give you minus by, and z cross y will give you x, right? So that is precisely why we have this matrix like this. So as a result of this, we can get that this is nothing but just omega, because omega is phi dot times z cross b. So that is a long roundabout way of deriving what the derivative of a vector is, and indeed it is omega cross the vector itself. Perhaps not so surprising because we've already obtained that result in the case of radius, but it's nice to be able to show it in a formal way like that. So let us move on to the next part of the lecture, where we will be able to show exactly the same thing, but in 3 dimensions. Please don't forget to do the quiz. Hello and welcome to the last part of lecture 14.3. So now we would like to figure out how rotations work in 3D. So we can write exactly the same thing, that bi prime is equal to aij of bj. And one thing that we will require is that during the rotation, the length of a vector is unchanged. So what that means is that b tilde times prime times b prime is going to be equal to the original vector b tilde times b. So because b prime is this, we will be able to write this as such, and a transpose of a product will be b transpose times a transpose times a times b, and this is the requirement, that this is equal to that. From here we make the conclusion that a tilde times a is a unitary matrix. That means that a inverse is equal to a tilde, and this is, by definition, referred to as an orthogonal transformation. So it doesn't change length, so this includes rotations and reflections. So from the fact that the length is unchanged, let's write this out in components to see what we can glean. So in components, this will look like aik times aij is equal to delta jk. And you can see that this left-hand side part is symmetric with respect to j and k, because it's the same exact matrix. So if we swap j and k, we're not going to get any change here on the left hand side. So it means that out of these, how many? 9 elements, because j and k can go anywhere between 1 and 3 inclusive, we actually have not all, but only the ones that are not affected by symmetry, so only the upper part of the elements that actually play in the role, because the other ones will be satisfied automatically if these upper ones are satisfied. So there are only 1, 2, 3, 4, 5, 6, only 6 independent relations. So the fact that the length doesn't change imposes only 6 independent constraints, not 9. That's because of the symmetry of this product on the left. And so this independent constraints means that we can now figure out how many degrees of freedom we have when specifying a rotation. So, question: how many independent degrees of freedom in a rotation? So let's look first at 2D case. Well, there we only have 1 degree of freedom, and that is phi, right? How about the 3D case? Well, there, in a rotational matrix, we have 9 elements, but we have 6 independent constraints. So we have 3 degrees of freedom in a 3D rotation. So that's all that's left for us to set. And these degrees of freedom will be our Euler angles. And this is precisely what we're going to introduce in lecture 15. Thank you very much for your attention. Please don't forget to do the quiz. And I'm going to see you in the next lecture 15, where we're going to be talking about the amazing, exciting topic of Euler angles and the motion of rigid body. See you there.